My name is Rob Wolfs, and I will be the host for the first keynote of today by Professor Theo Salet. Theo Salet is Dean of the Department of the Built Environment and full Professor of Structural Design of Concrete Structures. His research spans from parametric design tools to nonlinear numerical analysis of concrete, with a focus on 3D concrete printing. Theo, welcome, and it's very nice to be here on stage together.
Thank you, Rob.
Our research group is known for its work on 3D concrete printing over the past years, from small-scale experiments to large-scale applications like the bicycle bridge in Keynote. Looking back to the past few years, but also ahead, is there a future for 3D printing in construction, and what does this future look like?
Yeah, Rob, our nature would be to answer this question from a perspective of the technology itself, but I think we have to look more on the societal aspects of this matter. Our industry faces issues with sustainability, and with that comes also the degree of freedom in designs, and issues with respect to productivity, be able to make enough affordable houses for future generations. And with that comes the issue of digitization. That's the title of this presentation, Working Towards an Industry 4.0. And we're not the only ones doing that. If you look back in history, what happened, different industries already invented that idea to look how digitization could be helpful to improve on issues regarding these societal issues, as you can see on this slide. We as a group and more or less as a faculty as a whole work on that issue of digitization as well from different perspectives. So we work on digital twins. We also work on artificial intelligence tools combined with material tests and with algorithms to bring robots to life. So try to combine AI things with the issue of robotics. As a chair in our group, as you are familiar with, we focus on the issue of 3D printing of concrete, and this large-scale gantry printing robot, I think, is known to many of you already. And with that instrument, we made a first bridge in Keynote. And that was for the simple reason, coming back to your question for the meaning of the construction industry, to just try and have an effort in making something, show that to the industry and say, this is what we can do. Please reflect on it and tell us if that is beneficial for your industry as such. What we realized from this kind of work that we did, it was the first time we did it, that it is relatively difficult. It's not self-evident. It comes with a price because it's a complex system. You cannot just print whatever you have designed. Material, the design, and the printer needs to come together. It's more or less a complex system that has to fit together and make a full set system as such.
Okay, so I guess it's important to emphasize that 3D concrete printing and other digital fabrication tools can provide an answer to these challenges in society, but at the same time it comes with an added complexity, and we have to address this as well. You wanted to illustrate this vision with two projects. Why these two?
Yeah, I selected these two projects, a housing project Milestone that is currently being printed here in the city of Eindhoven as we speak, and a bridge project designed by Michiel van der Klei. And I selected these two projects to illustrate that our Faculty of the Built Environment is a typical faculty where built environment, buildings, and civil engineering is combined into one faculty. So I selected these two, and the second reason is that one is more difficult than the other, but I'll come back on that issue later on during this talk.
Well, then I hope you can tell us a bit more about these projects.
I would love to. Let's start with the building project. These buildings, and I guess you have seen the images before, mainly the important part is the plan view. If you have a look at the plan view, what we did is we approached the design from a perspective of that complex system that I just mentioned to you. And what we see here on the slide is that what we actually did is we printed corner elements, so volumetric elements, not a straight wall, but walls in a corner, curved walls, because they are stable in themselves. And they were printed on a slab. So actually what you have is a part of the slab of your building and a wall already on top of it, and that's a wall with a corner already in it. So it makes it very stable, it makes it easy for transportation. That's the plan, and in between these elements, you could place framework elements and put your roof on top of it, so that the load bearing capacity is both on the framework and on your printed concrete. That's the plan, that was the idea. And all of these elements are, can be reused again, of course, because you can place them in a circular kind of economy in different plans of different buildings again. If we have a more closer look to these walls, what we see now is on the left-hand side an example that you print an inner and an outer wall, and you connect them, for instance, with the snake kind of thing that we see very often in 3D printing and extrusion processes. But if you make a real house, at the end it must be comfortable as well, so you need to fill that in with insulation materials. Now, what you can see on the right-hand side is a first try for the fill-in, but imagine that that fill-in material could also be used for structural purposes, taking care of the shear capacity of the wall. Then you can cut down on the amount of concrete that you actually print. If that's the system that we are aiming for, it comes with a couple of questions. And for instance, in the fresh state, if you start to print this wall, it must be stable, and you want to optimize these sandwich kind of structures towards thinner and thinner walls over and over again, for reasons of sustainability. But then it must and remain stable during the printing phase, and your research work is a nice example of what we need to do in that case. The other issue is in the hardened stage, when the concrete is hardened, if you make it thinner and thinner, it comes with stability issues again. And again there, the presence of the insulation material should be beneficial and help the concrete not to buckle. So it's really a marriage between two materials here. At the end, if we make these walls, if you want to make it a system, you want to make them a system for real life buildings where people live in, you need to test them. And luckily, we are in a fortunate position here that we can do all these large scale tests to see if the theory that we come up with also works into practice.
Okay, that's very clear. But up to now, you've mainly discussed the design and the concept of Project Milestone. But you mentioned also that it's important to consider the material and the 3D printer. Can you elaborate on these two topics as well?
Yeah, I guess the message was already sent by the first keynote speaker, Robert Flatt, who had a nice formula that's saying that if you look at sustainability, you have to consider the amount of material and the amount of cement per unit of material and multiply that together and divide that by the lifespan of your structure. So talking about reduction of concrete, I guess that's why we print, that's the additive manufacturing part. But yes, indeed, you need to discuss the amount of cement per unit of concrete as well. In our group, we work on that issue, and it's our colleague, Sandra Lucas, who unfortunately cannot attend this conference here because she just gave birth to her first son. But Sandra is working on the issue of the materials, together with the design, because again, in a complex system, these two things come together. And her work focuses particularly on two things. The first is just sustainability from a perspective of emission-free concrete, making emission-free concrete. And on the second hand, of doing something different, and that is adding functionality to the concrete, so that the concrete no longer is only the load-bearing part of the structure, but maybe also is doing part of the insulation itself, or being there for electricity conductivity at some parts of the structure. So taking more than one function, which is also a way to increase on sustainability. And this is, for instance, an example, a more technical picture. On the left-hand side, you see a wall, just a traditional wall. Let's imagine it's 3 meters high, it's loaded, it's reinforced. But what structural engineers know is that the flow of forces in a wall do not need the full wall. Part of the walls are stressed in compression, part of the walls are stressed in tension, and in between there's hardly any need to have any material. So it would be a good idea to improvise or to improve on this one and come up with improvised solutions that give much more less concrete use. One typical way of working with that is, for instance, this. What Zishan Ahmed did, one of the PhD students that is about to graduate soon, he developed a grading type of material where material is deposited where you actually need it. So concrete that is strong and at the same time at another place It is just taking care of, for instance, the thermal insulation. And imagine if you go back to the picture of the sandwich wall, if we could just print a sandwich wall, but at different places in the wall could apply different types of properties of a material, you have a kind of a hidden structure that you can't see with the naked eye, but one part is doing the structural part, another part, for instance, is doing the thermal insulation. Making things like that comes again with a price, with a cost. So you really need to do research, because at the end you want to be sure that the right concrete is at the right place with the right properties. And starting from that perspective, that at the end the properties of concrete must be good, you need to think backwards, what is it I need to do in my mixing, in my pump, with my hose, to really get that done? And that's what Derek Bos, one of the PhD students now, is doing in his research here at our university. At the same time, you have to do something on your machine, on your robot as well. And this is one of the early things that we immediately did when we had our gantry robot. We mounted the machine so that we have always a fixed height of our next layer on top of the other layer, to be in control of that and avoid issues, for instance, with the poor bond that we heard a lot about already during this conference. Other issues what we do, for instance, to be in control is play with temperature, what temperature means on fresh concrete, and related to the stability issues, of course. And one of the most weird things that we ever did, and most of the time will do again in the future, I guess, is to be in control of fiber orientation even after printing by mechanical fields. Talking about that complexity, and maybe wrapping this part of my story up, is what we do is we do modeling, we do at the same time testing in the laboratory. But in this age, a third thing comes into the picture, and that's data. We're going to use data to add to that story and help us to solve the more complex issues. And that's your cup of tea in your research work.
Right, absolutely. And it was also Maarten Steinbuch, one of our keynote speakers on Tuesday, that said data is crucial. So we will have to start to combine numerical approaches to simulations with data-driven approaches like non-destructive measurements to be in full control of the process. And I think we can learn a lot by venturing into other fields and connecting with other industries to bring our technology one step ahead. Theo, before we move on to the next part of your presentation, I see some questions have come in the chat, and I would like to address a few of them to you. The first one is by Kees Lehmeyer, and his question is, will we shift from the design of a product towards the design of the process?
It's a definitely yes. So that's the case, because what we are normally doing, and there's nothing wrong with that in our industry, is to work towards a unique product. And we have to do the designing, we have to do the construction part. We have a difficult, a very long supply chain to get that done. And we need to do it over and over again, because we're working on unique objects. That's the nature, I would say, of our industry. And I fully agree that we need to move on to the next phase where the process becomes much more important, working towards standardization of things. And that doesn't mean making them more boring. Yeah? I fully agree.
Okay. A second question comes in from Tim Wengler from the ATH. Theo, are concrete color printer plans still on the horizon? Printing multiple materials?
Yeah, that's an interesting one. Yes, I think we have to, more or less. And if color means not red, green, and blue, but different types of materials, why should we do everything in concrete? That's the question that would raise back to Timo, because there's no need to do everything in concrete. So let's make use of the material to its the way it is best. Concrete is good in compression, it's fire resistant, but let's try to use different and multiple types of materials and use the best out of each material from a sustainable perspective to come with valuable solutions for our society.
Okay, thank you. So let's go back to the system for a moment. You mentioned the sandwich structures as a concept, as a system in Project Milestone. But is this sandwich principle then the system for 3D concrete printing that we will move on with from now on?
Yeah, I raised that question myself a couple of times, and we heard from the lecture of Maarten Steinbuch earlier during this conference that he said that accuracy and speed are key. And he mentioned layer by layer, centimeter by centimeter. He challenged us to make speed. So what we've tried, and is something that you also said during his talk, just try something and come up with some alternatives and surprise maybe industry with that in order to find out if it meets their challenges. And this is an example. What you see here, for instance, is again a wall, but now not a sandwich wall, but on the left-hand side you see just a straight wall. What we did here is we intend to print that wall not vertically, but we intend to print it flat, so in the plan view, and then simply rotate it 19 degrees. If you do so, there's no need with the printer to print all these lines rectangular, as you can see on the left-hand side picture. You can make any kind of shapes, like the middle one. And the advantage of that is that you can start to optimize your flow of forces. And that means that you can cut down on the amount of material that you need. And normally people would do that maybe in a type of lattice kind of structure, but then you have to cross each node with your printer multiple times. And in order to reduce that, we come up with a more Voronoi picture like this, a pattern like this. But again here, you need something in addition on top of a lattice structure. You need an insulation material to take care of the shear forces in a structure like that. So similar to the sandwich element, where the insulation material, and that's maybe referring back to the question of Timothy, you need a second material here to take care of the shear forces. But at the same time, that material can take care of our thermal insulation. We call it stringer panel methods. It's a simple design tool, and it's very simple to design with tools like this. From that, we came to the idea, okay, let's move on and not optimize only from a structural perspective, but also optimize these walls from a perspective of, for instance, lighting, and make walls, facades, that are not structurally optimized only, but also optimized with respect to the amount of light coming inside our buildings. And with that came this picture. But you're questioning me, Rob, but actually this is the work of your studio this year. So I challenge you to explain the picture yourself.
Okay, I will. This is actually the excellent teamwork of 3 of our master students, Tessa, Irma, and Jelle. And what you see here from the top left to the bottom right is an optimization for 3D printing towards multiple criteria. So we start with an initial domain, and after a numerical analysis, we eventually end up with an optimized geometry. And this geometry takes into account both stress constraints, but also, like you mentioned, the daylight entrance. So we get bigger regions of openings, and we try to push them towards the top of the wall, so we maximize the daylight in the room. And the next step is to transfer this into a solid geometry and to generate print paths. And for that, we use evolutionary algorithms to select the best, the quickest print path within millions of solutions, making sure that also in the nodes, print lines do not cross, and that we have a proper anchorage of, for instance, reinforcement in these elements. So I think this is a very promising development in our field.
And again, Rob, I think you have to combine that again with the type of material that you use and the capabilities of your robot to make it a complex system again.
Absolutely.
Yeah. Yeah. Having said that, I think there is a downside to this thought, because before we are becoming too enthusiastic about it, there's always a but. In this case, it's about the joints. The advantage of working on the milestone projects with these corner elements is that there are no joints, only the joint between the window frame and the concrete elements, but that's a non-structural joint. But if we work on wall structures and on slab structures, and we need to connect slabs and walls to walls together, there must be connections that are capable to carry loads. Now, this is a kind of an example of a dome that we made a long time ago already. It's called the Turtle for a reason, I guess. And the connections are relatively simple because a dome by nature is stressed in compression, so you expect only to have normal forces in the connections like this. However, if we move to the other structures that we just showed, the wall elements, we need to have connections that can carry loads in compression, tension. but also in shear, and hope maybe in the future in bending, but let's make that the next step, I would say. And that makes it more complicated. So we really need to look after that. One remark to this turtle is that take care if you design dome-shaped things like this, because with 3D concrete printing you want to make things much more light, and then the natural shape of a dome is not a dome anymore, because the self-weight is not governing, but the wind load becomes the governing load, and the shape of the dome immediately starts to differ.
Okay, but Theo, you don't have to be a professor to know that concrete is good in compression, but not so good in tension. So when you start to introduce connections like this, and also when we start to optimize, we will have to address the issue of reinforcement.
Yes, Jimmy, I will address the issue of reinforcement. And we already addressed it a long time ago. Zishan Ahmed, I introduced him earlier during this talk, developed this tool to embed the reinforcement wires immediately during the print process. But that's one, making the tool is step one, but then the next step, of course, is to go further in this field and investigate the true meaning of the reinforcement systems like that for 3D printed concrete from a structural perspective. And that's the research field of Freek Bos, looking after the structural properties of reinforcement. And of course you have to combine that again with the material, because one comes with the other, so the complexity is here again. And his research work is on finding out what the true meaning of reinforcement systems like this is in terms of bond between concrete and steel. It started with something like just confinement and is now developing towards things like real bending structures, where the reinforcement needs to have a good bond with the concrete, as you can see on the picture here. But that's still reinforcing in the direction that we are more or less familiar with already. The next step that he takes, and he takes that step together with a PhD student, Laurie Haas, that you met before in this conference, working on the perpendicular direction. So that's reinforcing layer by layer perpendicular to the layers. And this, in this example, by using a screw type of reinforcement. Another idea of working on reinforcement, but okay, we can argue whether this is reinforcement or an improvement of the material, of course, is the introduction to introduce fibers into your matrix. The picture on the right-hand side, an old picture from the work of Zishan that he did embedding the fibers in the structure, is now being followed up by Karsten Nefs, another PhD student that you have seen here on the stage during the conference already. And he's working now on totally different types of fiber reinforced concrete, the ECC materials, where not only the fiber orientation matters, but where also the fiber shapes matters, because they're not straight anymore. And what we always want to do, and I told you that in the beginning, try to do experimental research, do laboratory research, at the same time make numerical models and have that data AI tool available. And he is, for instance, here using an AI tool to get grip on the image capturing and making models from that, using neural networks to create these structures, as you can see here. And this is one of the examples of the numerical models that we use. This is just an example of one fiber being pulled out of concrete using cohesive zone modeling. And that's something that, to my pleasure, I saw during this conference as well from multiple authors working on issues like this. And then, maybe it's a bit tricky to say, but working on reinforcement in strut and tie and kind of structures, using the tensile part as well, in wall elements is maybe a small step towards using reinforcement in slabs. And this is a kind of an example of an optimized slabs, and we have seen multiple of these examples from different presenters during this conference and upfront as well, and I'm most happy with that. What we did here is we try to we make it reinforced as a slab, we made it pre-stressed as a slab, and we tried to make numerical design models that not only took into account where to place the material, but also how to deal with the pre-stressed ducts. So the level of pre-stressing was determined by the position of the load. So if you stand in the middle of the slab, the pre-stressing is differently from the moment that you step on the slab, just at the edge. And this technology is promising, but it's a little bit ahead of us, I would say. And one of the interesting things about this type of optimization is that we try to make use of the concrete to the best of its capability. So stressing compression, yes, we benefit that, but if the material is stressed in tension, yeah, we punish it a little bit. So that kind of algorithms are built in these design tools.
So from floor slabs and beams, it is not that big of a step towards bridges. And one of the first projects that you showed was also a bridge project. Do the same principles that you've showed us up to now also hold for such structures?
Yes, they do. But I have to made you a promise, so I have to keep my promise. Is it more difficult or more simple? And to my opinion, but it's just an experience of a couple of years, it's maybe more easy. If you look here together to the nice bridge designed by Michiel van der Klei, we try to realize this bridge, made a mock-up and see if it actually holds. So actually here again we had a concept. The concept was this time print the cross sections. So you print the cross section of the bridge, and in this case it's not the bridge in Keynote anymore with similar cross sections, but it's different types of cross sections that we have here. Each cross section was printed from a parametric model, obviously, and after that flipped over for 90 degrees and stacked together. In this mock-up, we glued all the elements together, but in the future, for reasons of circularity, of course, we would love to have cold joints so that everything can be reused again. So the principle is relatively simple. You print in a cross-section, you flip them over, and you stress them together. So it's a relatively simple concept, I would say. I showed you a big picture with a large-scale test, but everything starts from small. If you do a project like that, you have to start understanding your material properties first. So that's the research work that you did yourself, for instance, and many others here at the conference, joining the conference, finding out the properties of fresh material by different tools, and finding out the properties of hardened materials and interface behavior as well. That's key. You need to know that before you can make any design and rely on your structure. And the final step, yeah, that's the step where you start to really test a long-scale bridge. And as I showed you, designing from the house that we made for Milestone, and going from Milestone to the different types of walls, you can go from that type of bridge to this type of a bridge. And again, the story of doing things big and doing things small matters here, because we on purposely ask you to be in this picture to make the bridge look a little bit bigger than it actually is.
Well, thank you, Theo. Perhaps you can share a serious note as well to end this keynote.
I will do. And I think I like to do that. First of all, before I do that, I would like to tell that everything that I'm saying here is a result of a series of people that I just introduced, and that we are really in the fortunate position that we can even extend our group with the positions that you can see here on the screen. And it has a meaning that I show that to you. It's because I'm really proud on the team, but at the same time, it is because we as a team would like to stay with you, not only during this conference, but also the days and the months after. What we have experienced here, doing this conference in a online fashion, it was not only a hassle, but it also brought us something. It showed us that it's possible to be live together from a distance. And what we aim for and what we really offer to you, and hope that others will follow this idea, is to meet on a regular basis, exchange ideas on tests, maybe even put the cameras on the test facility, show the tests immediately so that you have a first impression on how things going from another part of the world, and have the data available as raw materials so that you can study them yourselves. Another idea is to exchange all the test setups. We have seen so many nice and wonderful test setups using this conference, but I would like to use them myself. And as a first step, I would say all the things that we use as test setups are available for all the other researchers worldwide as well. And that same counts for all the design tools that we develop. I'm a bit scary to share them, of course, because they're not perfect yet. But maybe that's the best to do, to share these products and ask our fellow peers to make them even better.
Okay, thank you very much, Theo. I think that's an excellent ending of this very interesting talk. We still have some time for questions, so let me take a look if some questions came up in the chat. The first one appearing is by Juliette Beckering, who is asking if the integration of services like electricity cables, water ducts, heating devices, and so on is in sight for 3D printed walls within this complex system.
At the moment, the answer is no. In terms of can we start working on that and use technology, use knowledge that is already available to really start working. No, that's not. But we are just a phase up front, I would say. We start to work, Sandra Lucas starts to work to develop these materials right now. That means that we need to do some research on developing materials that have these properties. Next step is we need to make them printable. And the step after is we need to apply them to something. But I would like to challenge Juliette and ask her to join us and to see if, from a design perspective, we can make designs that are made to make use of these materials. So that's where the complex systems comes in. This doesn't make totally no sense, us making new materials, if from a design perspective, there's no designs where they can be used in.
Exactly. I also see some questions coming in regarding the insulation material. If we are still using a conventional material right now, but what are the other answers in the way of insulation in the future?
Yeah, that's an issue. And maybe you saw that from the pictures that I showed, that we still use relatively environmental unfriendly insulation materials simply for a reason that we don't know for others. Mm-hmm. So I'm really in a need for other researchers that can help us, other research fields that can help us to make materials, insulation materials that are much more nature friendly on one hand. So I'm really in a need for help in that perspective, and you can imagine more of us are. The second thing is that we still connect them now to our concrete. And that's what I want to get rid of, mm-hmm. Because in a circular kind of an economy, if you use the insulation material together with the concrete, at the end of the lifespan of the structure, you want to separate both materials and treat them separately again. If you not use the element as such, as a total, again, and reuse that again. Yeah. So it's two things. We need to work on the materials and have better insulation materials, and we need to work on the connections to be able to separate them.
Okay. So the nice thing is that in my room B, which I was hosting during this conference, I actually saw quite a few examples of lightweight concrete and foam concrete that were already printable. So I guess that's one of the first groups to team up with and see if we can combine these materials.
If we can make them a little bit ductile, that would be happy.
Right. Okay. One more question coming in regarding the structural simulation. So you mentioned the digital twins a few times. What are the key differences in structural simulations of 3D printed elements compared to conventional ones?
And is the question about the design of the structure or the research part, do you know?
I think it relates to the structural design.
Yeah. I think the big question here is how to design printed structures.
Exactly.
Is there a code for it? You have seen a couple of pictures that I showed, examples that we showed. The bridge in Keynote, for instance, and the other bridge in Nijmegen, the house project in Milestone. What we always try to do is have a permit. So that's our aim. And that makes it a huge challenge because all of a sudden you need to design, and if I say we need to design, it's our industrial partners who need to design these buildings, and they're asking for how does this comply with the codes. The solution so far is not that difficult because our codes, particularly the European codes, I must say, are not related to a kind of a manufacturing strategy. It's different in different parts of the world, so I should take care of my words here. But European codes are not. So we can make use of the codes that there are. And most of it will be on really knowing our material properties very well. And then from a structural perspective, look very carefully, what is it that my structure needs to do? And what is it that I expect that concrete that is made in layering by layering methods will be different about? And that's what you have to test. Most of the time we show these large-scale tests, and that's just to play safe, because we are the first one and we don't want to be the spoiler for all the rest. But eventually, at the end, it should not be doing all these large-scale tests, because then we make a bridge twice, once to demolish it in our test setups, and once for the real bridge, and that's by far, of course, too expensive.
And not very sustainable.
Yeah, I agree with you.
A final question, it's a bit of an open question to you. What are some of the future developments that you would wish to see expand in the field? So let's say we are a few years from now, what would you like to really have achieved?
And then I come back to the way I opened this. I could answer your question from the perspective of the technology and say, I would love to have a better robot, I would love to have a better mortar or a better design. But I think, and that's what I really hope, that it is really on the integration of this, on that complexity. What I hope is that we are able to make showcases of bridges and small houses like we're already doing. And that was the huge joy of this conference so far, that we are capable to make these examples, show that to our society, to our industry, and together with them, both just the people who have to live in these houses and the industry, work on examples and find out together where the benefit of this technology is. We love to work on this as researchers. And you can see in the conference people being here early in the morning at 5 o'clock and not wanting to leave at 12 o'clock in the evening. So that's such a strong signal. But if we can combine that, and that's my answer to your question, with looking for the real need to have an impact, that's what I wish for ourselves in the next future.
Okay. Thank you, Theo. I think these are perfect closing words for this keynote. Thank you for being here and for answering all of these questions.
It's my pleasure, Rob.
With that, we have come to the end of the first keynote of today.